Space telescopes have a ridiculous problem. We want them bigger, way bigger. But before they can look billions of light years into space, we have to somehow cram the entire thing inside a rocket. And rockets aren't exactly known for having extra trunk space. That's why NASA researchers have been experimenting with an idea that sounds completely backward. Don't launch the giant telescope mirror. Launch liquid and make the mirror after you get there. Yeah, that got my attention too. Here's why this could be such a big deal. When you're building a telescope, the mirror is everything. The larger that mirror is, the more light it can collect. More light means astronomers can see objects that are dimmer, farther away, and harder to detect. That's one reason the James Webb Space Telescope is so powerful. Its primary mirror is about 21 feet across, but even that enormous mirror couldn't simply fit inside the rocket. Engineers had to divide it into 18 hexagonal segments, fold parts of the telescope for launch, send the whole thing into space, and then unfold it. And if you've ever watched footage of Webb deploying, you already know how nerve-wracking that was. There were hundreds of things that had to happen correctly, because it's not like somebody could pull over and fix it. Now suppose we want a telescope mirror that's 50 feet across, or 100, or eventually even larger. At some point, folding everything inside a rocket becomes an engineering nightmare. So researchers involved in NASA's FLUTE concept, Fluidic Telescope Experiment, started exploring another possibility. Liquids naturally do something incredibly useful in microgravity. Surface tension pulls them into smooth shapes. And smooth, curved surfaces are exactly what you need for optics. Instead of manufacturing one gigantic solid mirror on Earth, protecting it during launch, folding it into a rocket and hoping everything deploys perfectly, you could potentially transport the raw material in a much more compact form. Then form the optical surface once you're already in space. Think about that for a second. We're basically talking about manufacturing part of the telescope after launch. Researchers have tested the basic idea in several environments, including neutral buoyancy experiments underwater and experiments during parabolic aircraft flights that briefly create microgravity conditions. And they've even tested fluid behavior aboard the International Space Station. The reason water testing helps is clever. Researchers can use liquids with matching densities, so buoyancy effects are minimized, allowing surface tension to dominate more like it would in microgravity. Under the right conditions, the liquid naturally forms a smooth curved surface. Then that shape can potentially be hardened into a permanent optical component. And that's where this goes from weird experiment to something potentially enormous. A traditional telescope mirror gets harder and more expensive to manufacture as it gets larger. It also gets heavier. And anything going into space has to survive vibration, acceleration, and launch forces. Liquid doesn't care about being folded. It doesn't need hinges. And you don't have to polish a gigantic piece of glass on Earth if the optical surface can essentially form itself in space. But don't start waiting for NASA to pour a swimming pool into orbit next year. There are major problems left to solve. The finished surface has to be extraordinarily precise. We're talking about optics, where tiny imperfections can ruin the image. Engineers also need reliable ways to control the liquid, create the exact shape they want, harden or preserve that shape, coat it appropriately, and integrate it with the rest of a functioning telescope. Then there's the bigger challenge, building all of that reliably in space. But the payoff could be ridiculous. Much larger telescopes could collect more light and potentially let astronomers study extremely faint objects. That could mean better observations of distant galaxies, more detailed studies of planets around other stars, deeper searches for atmospheres that might contain signs associated with life, and a better look at some of the earliest structures that formed in the universe. That's why I love ideas like this. Somebody looked at the problem and didn't say, "How do we build an even bigger mirror that still fits inside the rocket?" They changed the question. Why does the mirror need to fit inside the rocket at all? That's a completely different way of thinking. And space exploration probably needs more of it, because rockets aren't going to magically become infinitely wide. If we want truly gigantic structures in space, eventually we're going to have to get better at building things after we leave Earth. Telescopes could be just the beginning. We've already seen spacecraft unfold solar arrays and deploy structures after launch. Future missions could push much further toward assembling and manufacturing equipment in orbit. And if fluidic optics eventually work at enormous scales, one of humanity's most powerful windows into the universe might begin its journey. Inside a container of liquid. No giant mirror, no impossible folding puzzle, just raw material, a trip into space, and physics doing part of the construction for us. Which leaves one hell of a question. If we're no longer limited by what fits inside a rocket, how big could a telescope actually become?